you have to do this. So it just walks you through the experiment. Pre-lab has nothing to do with it. Pre-lab is per se, you read the experiment and then you write down the pre-lab. So the videos will always be open on Monday, like right before the lab or right after the recitation, sometimes like that. And then watch those videos before you go into your lab, do your lab. That will help you save time. That will give you an idea of how this lab should be done. That's all it is all about. And those were luckily recorded during the COVID time. So we're just making use of those COVID time videos to help you understand those labs. We did not make those labs per se for the labs. If you do not, you will be asked to leave to complete it. You need to have your pre-lab. So once done, return to lab and complete your lab. If you do not return, you cannot complete, and you cannot complete the lab and you will lose all the associated points. So you should have your pre-lab. Simply speaking, if not, you will be asked to leave the lab and then you have to finish your pre-lab and then walk in, and the time lost in this process is on you. They can't give you additional time because you missed doing something, right? So, and this usually is not the case, but it's better to specify it out there rather than I didn't know sort of a thing. So we just specify that. Now, example, if you have not done pre-lab 1 for this lab, you cannot complete lab 1 this week. So, and no excuses on this part of it. Recitation attendance is mandatory. There is a sheet. I hope you're passing it on for attendance. So there are 3 different sheets actually being circulated around. So please pass it on to the next person so they can sign it. And this attendance is mandatory, and I'll get this attendance onto Canvas right after our recitation by end of the day, before the end of the day today. And if you see a 0 for this lab recitation attendance, you cannot attend the lab this week. Unless you take permission from me, I'll let your TAs know that this person is not present, they do not have 10 points for the attendance, so they cannot attend the labs, and your TAs are familiar with it. They will know from me that you did or did not attend the recitation. Recitation is mandatory for this lab. Okay? So please be here for 15 minutes and then you can get the lab done this week. Now, once you have your pre-lab written, your TA will check that during the lab, as you're doing the lab, and initial it there. And then at the bottom of the page, there is an initial, they will initial it. So make sure that you complete your pre-lab. Okay? Now, I think you remember me mentioning about this worksheet, like the GDA weekly points. If you go to the syllabus, you'll see certain points associated with this section. So this GDA point sheet is applicable for this experiment 1 you're doing this week. Your GDA will assign you points based on 3 categories here. One is a general category, that is you're present, you're on time, you're following the safety precautions and all those things. And second section is, it moves into this. Second section, safety precautions, that you're wearing everything you're supposed to do, and then cleaning, keeping the labs clean. If you weigh something on the hoods, if you do something, make sure you clean them up, please, after you. So based on that, they'll give you points, and these are out of 10. And if any student doesn't get those points, they'll specify why the student has been deducted. Points have been deducted from that particular student. So in this, you have, I think, around 50 points, I think, overall you have for the GPA weekly point sheet. Okay, so make sure you follow all this. Again, the TAs have this sheet, so you know what they're grading it for. How many, what are the points given for? So you clearly know what it is. Follow this. Now, arriving on time is also important because points will be taken up if you are late. So labs start at either of these timings, either at 7:30 a.m., which is on Thursday, morning lab, and then 12:30, tomorrow's lab starts at 12:30, and every day we have almost 12:30 lab, except on Fridays, and 5:30 p.m. So whether your lab starts any of this time, you're expected to arrive and start the lab on time. That way everybody's on the same page and your TA can answer your questions accordingly. 2 different people on different pages. It's hard to do that. So deductions for being late and beyond. So if you're 5 to 20 minutes late, you lose 5 points out of your GPA points. If you're 20 to 60 minutes late, that is an hour late, then you will lose all your GPA points, and also in addition, you'll have 20% point deduction from your lab reports. Remember, lab reports account for 80 points. Every lab report accounts for 80 points. So 20% of that will be deducted just because you are late. So if you are late this week by 25 minutes, a 20% reduction, your first lab report will be given to you. It will be taken up, and those points will be, the rest of the points based on how you have written your lab report will be assigned to you. Now, no one later than 60 minutes will be allowed in the lab, and you'll receive zeros for all the GPA points and the lab report. So if any situation arises like this, an emergency, you should always contact me and your TA, CC me and email me and CC your TA, so that we can do something about it if, based on the reason provided and things like that. Okay, so please never be late, be on time, get your lab done and then walk out. If you arrive late, you will only have until the last person that arrived on time to complete your lab. There is no extension of time just because you are late. Because we have labs running back to back, we cannot extend something into the next lab. We have to finish in the time allotted and then so that the next lab starts on time. If there are any excused late arrivals, you must contact me first, and then based on what it is, I will accordingly work with you. It's on a one-on-one, case-on-case basis. There's nothing promised at this point, but just reach out to me and let me know what it is, and then we can do something about it. This week you'll be using some organic solvents, and all organic solvents, needless to specify, are to a certain extent toxic, some more toxic, some less toxic, but they are toxic because they are not water. Simply speaking, any organic solvent other than water is toxic, except water is supposed to be good for you. So you will be using organic solvents this first lab, this very first lab, which you probably have never used or probably have used. Doesn't mean that you should expose yourself to any of these organic solvents. Follow the instructions provided in the lab manual and what we are going through and what your TA says. Listen carefully and please do the experiment. They're very simple. This experiment is a very simple experiment to start off with. Now, each of you must have watched this pre-recorded videos, and then I have opened up this. You should have access to this already. So watch that video, it walks you through the experiment. This makes it much easier for students. The TAs will be able to tell if you have watched or not, because when you watch it and you understand it, you know what to do in a lab when you walk in tomorrow. It's not like you're figuring out things as you walk into the lab. You're watching this video, reading through the procedure, writing down your pre-lab, you pretty much know what needs to be done. You get into the lab, do as a pro, and then get out of it. If not, you're reading through a line and you're doing this, it kind of tells the TA that, no, yeah, they probably have not done their work, obviously, right? So, and they have been doing these labs for quite some time, so they pretty much can identify whether somebody has done their work or not. And it also takes your time. So you'll be there for 4 and a half, 5 hours, and you can finish these labs in 3.5, 4 hours. So it's like you're spending too much time on that, which you could have avoided. Now, what should I include for a pre-lab? That's a question which I commonly come across. A lot of students have this question, which is fair enough, so I thought I'll put what you need to include in a typical pre-lab. What should your pre-lab consist of? First of all, the title for the experiment, obviously, whatever experiment you're doing this week, right? The title, the introduction, what does that experiment deal with? Like, is it a technique, or you are learning, or is it a synthesis you're doing in this week's lab? What is that lab about? A small introduction about that lab. Now, the physical data table. Remember, there is a data table you need to fill in, the safety sheet, at the beginning of, you have some boxes, the solvents used, the toxicity, something, the chemical data sheet. So that table. And then you have to have your procedure. Remember, I told you the procedures in your lab notebook. Anybody has a lab notebook right now on them? So if you, I'm not going to open any page, that's it. So if you see this, any page there, so there is a bifurcation there. The page is divided into 2 halves. So you write down your procedure onto the right hand side, I guess, on this side. And then I get confused with right and left, so I'm just pointing it out. So you write down your procedure on this side, and then you write down your observations simultaneously next to your procedure. So when you're writing this lab report, when you're writing your conclusions, summaries, observations, and things like that, you exactly know what you did and what you observed when you're doing it, right? So procedure, observations. Procedure on one half of your page, and simultaneously leave some space between the procedure, one bullet point, like 1, 2, 3, A, B, C, however you want to. So that when you're doing this, add so and so. So what happened when you added so and so? So those observations should go following your procedure. That way when you go back to your room and then you're trying to summarize this, write your conclusions, you exactly know what you did and you exactly know what happened when you did those things. So it just makes your life much easier than recollecting what you did and trying to write on the lab report. an image or drawing of glassware and equipment. This goes back to techniques, experiments which involve techniques. Like for example, this first experiment, which is recrystallization and melting point, is a technique-based experiment. You are learning the technique of recrystallization, you are learning the technique of melting points, how to get a melting point for any given compound. So these are techniques. So for these techniques, you usually draw an image of a glassware which is used. For example, I would draw a picture of, say, filtering, the filtration which you do in recrystallization today. So the filtration setup, which I think your lab manual also gives you, and I also have it on one of my slides. I'll point it out when I get there. So any glassware diagram, like what are you using it, which explicitly is used for that particular technique or that particular experiment. But there are some labs which are synthesis based. Like for example, I've labeled them. Like lab 2, 4, and 7 are synthesis. Lab 1 and 3 are technique based labs, which is lab 1 this week. So for these reactions, for these experiments, experiment 2, you'll write down the reaction. If there is a mechanism, you'll write down the mechanism in this category. Are you with me? So based on what lab it is, you'll include this. So that goes into a pre-lab. This pretty much summarizes the pre-lab. And if you kind of listen to what we are doing here, you pretty much have everything sorted out. So you know what to do when you get into a lab. You've written down the procedure, you have your image, you have your physical data table, you have your introduction, you know what the experiment is all about. Watch the video and you're done. Go into the lab, just get your experiment done, and then write your observations, write your calculations, and then you should be ready to write on your pre-lab report. That's as straightforward as it is. Any questions? This is something which I included because I saw like a lot of students having a question about what goes into pre-lab. This is all goes into pre-lab based on what experiment it is. Okay? Now let's jump into this week's experiment, which is recrystallization, and the second half of it is melting point. Let's finish with recrystallization, then we'll get into melting points. Okay? So recrystallization is something which is very, very commonly used in organic synthesis. Anybody who is doing an organic lab, or if you're working as an undergraduate in an organic lab, recrystallization is the simplest technique which every undergrad will be trained in, usually. And we are doing the same thing in this lab. So what does it do? What is the utility of this recrystallization? Recrystallization helps you in separating a solid from its impurities. That's all it is. So whenever you have a solid trapped impurities with it, so recrystallization allows you to separate those solids with the impurities. Usually that's what we do in this. So it's a technique for purifying solid compounds that contain a small amount of impurities. Obviously impurities are supposed to be little in much lesser quantity than your solid itself. Right? Now the assumption we make in doing this recrystallization is that they both, the solid you're trying to purify and the impurity you're trying to purify it from, both of them are soluble in the solvent you're trying to use for recrystallization. Right? So they may dissolve in a given solvent. And what is this given solvent? That is something which you will figure out in the lab. So for the compound, first of all, you will do a known compound whose solubility is known, everything is known. You just follow the procedure, you do it. Then you will be given an unknown compound. So you will figure out what solvent needs to be used for that and how to recrystallize. Because you have done one experiment, one part of your lab with a known compound, you're familiar with the technique. The second half of it, you'll be given an unknown and you'll run the same procedure with your unknown. Right? That's how you do this lab. Now, the assumption we are making here is both your solid and the impurity are soluble in the solvent, but to a different extent. And that difference in the solubilities is what we are going to exploit for separation. So, but not to the same extent, and that is known as solubility. So your compound is more soluble or less soluble, your impurity is more soluble. One of them should be more soluble, the other one should be less soluble. And that is what we make use of. This difference in solubility is what we make use of to separate those two compounds. Your pure compound and the impurity you're trying to purify it from. Let's look into this. So solubility, as you're familiar with, is ability of any solvent to dissolve the solute. Solvent is something which is in larger quantities. Solute is something which is taken in a smaller quantity. Like if you say salt water, water is your solvent, salt is your solute, isn't it? Sugar, water. Sugar is your solute, water is your solvent. Larger and smaller water. Solvent versus solute. So solubility is the ability of the compound, usually referred to as solute, to form a solution with other substance, other compound or other solvent. And that is usually referred to as the solvent because it's taken in larger quantities, relatively. So what are we doing here? You start with a beaker or your test tubes, and then say I have X and Z, these are the two compounds, and I have water. So I take them, and remember this beaker is at room temperature. I'm not heating, I'm not cooling, I'm not doing anything to it. It's at room temperature. Now I take these three, then I take water, I take my compound X, and I have my compound Z. And everything is soluble at room temperature. It's soluble. You can see compound X in the solution, and you can see compound Z in the solution. Two different compounds, right? One is a compound I want, the other one is an impure. Whatever I don't want is an impurity. Everything is soluble at room temperature. Fine, sounds good. Now, are these both soluble to the same extent? What does this picture tell you? Isn't one compound more soluble than the other? The amount of quantity you see, isn't X in larger amounts than Z? Do you see that? Does it visually show that, the picture there? So you have of the compound X and Z. Isn't compound X more soluble in water than compound Z? Can I say that from this picture? Yes, no? Can I say, just by looking at the picture there, depiction, the way it is drawn, at room temperature, can I say compound X is more soluble in water than compound Z? Can I? Is it a safe assumption? Why not? Why not? If yes, okay. If no, why? Either ways. Trying to have a conversation, trying to have something more interactive. What is it? What do you think? What it is?
Because we don't know how much of compound X and Z were in the result to begin with.
Say I don't have anything to start off with. It's just pure water, and I'm taking my compound X and compound Z, and that's how I see it. Let's assume, to answer that question. That is a scenario which I should consider. So to answer that, so I did not start with anything. It's just water. I dissolve X and Z, and the picture tells me something. So if that is the situation, would you agree that X is more soluble than Z? Would you agree? Okay, fair enough. Any other assumptions we should make? Okay, to omit all these questions you might have, X is more soluble than Z. Let me put it that way there. So this picture kind of depicts that you have more of X, more species of X than Z. So I would say X is more soluble than Z here at room temperature. Now what am I going to do? Before I do something, water is a solute. I thought we took three compounds here. Then why do I keep saying water is solvent and not solute, and say X and Z are solutes, but water is not a solute, it is a solvent? I thought we just defined it. Isn't water in larger quantities than either compound X or Z? Isn't water in a much larger quantity than either X or Z? Isn't it? So anything which you take in large excess is known as a solvent, not a solute anymore. Okay, anything which is taken in large quantities is always referred to as a solvent and not a solute. Solute is something which is taken in a limited quantity. Large excess is a solvent, so water is a solvent. So this was at room temperature, where I had excess of water. Relative to X and Z, I took more of water, so that's a solvent. I had X and Z soluble in that water to a certain extent. So I took this from room temperature and cooled it to 0 degrees. Now you see the temperature. And how do I do that? You take ice water. You take a beaker with ice and a little bit of water, and you take so much water to not to dissolve ice, but to fill the gaps between ice blocks. When you only take ice, remember there are gaps between ice chunks, isn't it? You add water to fill in those gaps, and that's what brings you to 0 degrees. So you take your beaker with water, compound X and compound Z, soluble at room temperature, put it into the 0 degrees. And what do you see? Where is my X? Is that my X? That is water, obviously, right? That's water. And there is X. X has reached down to the bottom. It has what is known as fallen out of solution. It was soluble in the solution, isn't it, at room temperature? You remember? Now it is as if it just fell out of solution. It just is a solid at the bottom. Whereas C, as you can see, is still in the solution. It has not fallen out of solution. Are you with me? So X has fallen out of solution just by the color code. I'm calling that. And Z is still soluble in water. Still soluble in there, in the solution. So now can I filter this and get my two compounds separated? If I filter this solution right now at 0 degrees, filter it off, would I have my solid on the filter paper and this liquid which still has a Z dissolved in it? Z is still dissolved in the solution, isn't it? So Z is filtered out. It is in the filtrate and the solid is on the filter paper. Do you agree? That's all it is. Now your Z, you have separated Z from X, whatever those X and Z are. That's the technique. So you dissolve both at a certain temperature, you cool it so that one of the compounds falls out of solution, the other compound is still soluble in the solution, filter, separate them. Does it make sense? Does it make sense? That's the simplest way to put this technique together. The process is recrystallization. This is recrystallization concept behind it. So, compound X and Z are soluble in water at room temperature. RT stands for room temperature. But when cooled to 0 degrees, X falls out of solution. That's what we call it as. It comes out of solution, forms a solid there. So while compound Z still remains soluble. That's the process of recrystallization. You have recrystallized compound X using water as your solvent. That's the technical way of defining this recrystallization. You have recrystallized compound X using water as the solvent for recrystallization. Right? Every compound, based on what the compound is, can be recrystallized from a solvent. It can be water, it can be ether, it can be DCM, it can be any solvent. And that's what you need to figure out with your unknown compound. For a known compound, you'll be given everything. This is the compound, this is a solvent, this is how you do it. But unknown, you need to figure out all this. And that's where it takes time for that part of it. Any questions so far? So you are familiar with, I'm assuming you're familiar with precipitation. So precipitation is just getting everything out of solution. Now remember, we are not getting everything out of solution in recrystallization. You are selectively getting one thing out of your solution. The other thing is still in the solution. If it is precipitation, everything, X and Z, both will come out of solution. That is the difference. Precipitation versus recrystallization. Recrystallization is you are focusing on, no matter how many mixtures you have, you are getting one compound out of your mixture. The desired compound, what you want. Versus precipitation, everything out of solution. There is a difference. That's a huge difference. Now, why do we do this? Why is, I told you, in most of the research labs, recrystallization is done on a very regular basis. And if the lab has an undergrad, usually this recrystallization thing is given to an undergrad. Okay, please go ahead and recrystallize this. Of course, the graduate student walks them through once or twice, but later on it's not a graduate who do all these recrystallizations. Why is it so important? It is because when anybody does a reaction, not all reactions are 100%. Obviously, if that is the case, our lives would be so simple. But that's not the case. You start with, say, 100 grams, you probably, depending on what reaction you're talking about, you probably will end up getting 70, 80, 90%. But you still have 10% of impurity. Say the yield is 95%, you still have 5% of something else. It's not a pure compound. And why is this essential? Remember the medicines we take, the aspirin, the ibuprofen, any medicine you name, are all synthesized. They are made in companies. They are not natural products, isn't it? They're not, you don't take a leaf and chew it to get to this. It was older days, but you just now have a pill which is a pure form of it. A pure form. How do you think they get to the pure form? Removing all the impurities. To get to that product, they have run a reaction. Got that, but along with that there was something else. They purified it. So that you're not taking all these impurities into your body and see what happens. We don't do that. We don't do that. None of us do that. We don't do that. And that is the reason why this purification, recrystallization is a purification technique which is very essential, which allows you to do that. get a pure compound. It's important in a bigger picture. So now, so this is a reaction where you're starting with compound Z. You ran a chemical reaction. Compound Z is converted to compound X. Fine, works awesome. Not that much. So do we get 100% of the compound out? No, hardly ever. Very rarely you do that. Trust me, it is never happening. Never happening, almost never. So ultimately, the product you obtain contains a little bit of other products, other things. You have your desired compound, but along with that, you also have all the other things which you need to get rid of. And we use recrystallization for that purpose. So if you see how it is useful, it is very, very useful. Same thing. You take your water. I'm using water as my solvent. You don't necessarily have to use water. There will be other solvents you use based on the solubility. So you take this solid which you obtain from this reaction, which contains both some amount of compound Z, not reacted, and the product which you got. Okay. So let's say I want to separate them. So what I do is I choose the solvent based on those compounds. How do you know? You test them. You literally test them. You add the solvent and see if it is soluble or not. There is no other way we can see this. Okay, you just check, okay, it is soluble, it is not soluble, it is partially soluble, it is completely soluble. So you test them, you physically test them. And then you choose your solvent. In this case, I have chosen water. And again, you add water. How much do I add? Just keep adding water? No. You add so much of solvent so as to dissolve your compound. Just the bare minimum needed to dissolve your compound. Once you see a compound is soluble, stop adding any more solvent. Are you with me? Because if you have excess of solvent, your compound remains soluble in it all the time. Remember, at some point you need your compound back, don't you? Don't you want your compound X or Z, whatever you want? You don't want it to be soluble in the solution. You want it to fall out of solution. If you have excess of solvent, that falling out never happens. That is a major problem. One of the setback for students doing this lab this experiment in the lab. They add, I did everything, but did you add just the bare enough solvent, or did you add excess of solvent? If you add excess of solvent, your recovery will be very little. You just need to add the required amount of solvent. One tip you should watch out for. Just enough to dissolve. Because if you do more, it will remain soluble in the solvent. You will never get your compound fall out of solution. That is why you need to dissolve it in bare minimum amount of solvent, as much needed for dissolving. Okay. Now I followed all those. I have my X and Z dissolved in the solution. Fine. So this is at room temperature. Both of them are soluble. How do I get my X or Z separated out? But you're doing this at room temperature. Cool it down so that one thing falls out of solution. So you need to cool it down. Just leaving at room temperature, both of them are soluble. Cool it down to ice, into ice bath, and then you will see one of them falls out. Now filter and then get your compound, whatever your desired compound is. Either your desired compound is in the filtrate. Remember, when you filter, the liquid you get is the filtrate. The solid you have is the solid, obviously, isn't it? The filtrate is something which you filtered out. So either you have your compound in the filtrate or you have the compound in the solid, as a solid. With me? But either way, you have separated your two compounds. So you can filter and then you can get your compound X, pure compound X, if that's what you're looking for. Now, so this is, remember when I was talking about pre-lab, I was talking about the filtration setup. Here it is. You can replicate this picture as it is. That is a filtration used. Now, you have this Erlenmeyer flask. This is Erlenmeyer flask with a side neck, what we call it as, in your drawer. The drawer when you checked in. So what you do is, this side there with the tube, that is attached to the tube from your water circulation in the hood. Hood has a water circulation, here will show it. So there's a tubing which goes into it, you put that there. Turn on the water, it creates vacuum. And then when you pour it, it just sucks the water through. Okay? But there's a small technique you need to follow, your TS will walk you through. So that makes this filtration go faster. Then gravity filtration. Gravity filtration is take a filter, you put your funnel, you take a filter and then pour it. Just the gravity. it takes a longer time for you to dry this. So this is suction or vacuum filtration. Vacuum filtration is much faster. So you do a vacuum filtration, wherein you have this aluminum flask with a side arm. This is hooked up to the tube in your hood. There is a vacuum tube which your TV will point out. You put it in, turn on the water in the hood, and then it creates a vacuum into this. And when you pour it, all the water gets collected into your aluminum flask with the impurities. And then you have your solid on the filter paper. But before you do this filtration, make sure you weigh your filter paper and write down the weight of filter paper. Are you with me? Because now, after you're done, your solid is on the filter paper. Now, when you weigh it, you can subtract the weight of the filter paper from this, which will give you the weight of the solid. Am I making sense? You do not forget to note the weight of the filter paper before you put it in there. A lot of students do that. Then what you have to do is scrape off this solid, then weigh the filter paper, and then weigh it. It's an unnecessary thing you could have avoided. Just be a little vigilant. So can I just do it at room temperature to 0 degrees? Usually room temperature should work, but it takes longer time. It takes way longer time. So what we ask you to do is, instead of room temperature and 0 degrees, we ask you to heat it up to a certain temperature. So that heating kind of facilitates in making this compounds soluble, much more faster and much more efficiently. So instead of room temperature 0, right, we are going to a higher temperature and then to 0. Just a little warmer. Doesn't mean that you're boiling it. Just a little warmer. So at hot temperature to a 0 degrees. Now when you're heating it, when you're warming it or when you're heating it, you do not take from that heat to put it into ice bath. Oh no. You know that, right? If you're really mad at somebody and just want to do it, you'll have to pay for the test tube later on. But yeah, you don't have to do that. There's other ways of doing it. But not in the lab. Don't show your anger or anything in the lab. Nah, not worth it. So the test tube, when it is at hot temperature, get it to room temperature and then cool. It's more about the technique than anything else. The lab is very simple. It's just the waiting time. Be patient with yourself. Be patient with the TAs. When they say follow the procedure, please follow the procedure. And you will master this technique just like that. Now coming to the solvent. How do I choose the solvent? Remember, we chose water. I was choosing water every time. Do you choose water like a solvent for everything? No. For organic compounds, we generally don't use water, but there are cases where we do. So what is this ideal solvent you use for recrystallization? How would you know what to choose? What is the solvent I should choose for recrystallization? So the ideal solvent is the one which dissolves the target compound at warm or high temperatures. Again, how high? But at low temperatures, it has low solubility. That is the thing. So you're dissolving a compound, it's not soluble, you heat it. When you heat it, it is completely soluble. And then when you cool it down, things fall out of solution. Ideal solvent. It is not soluble, you heat it, still not soluble, not a good solvent for recrystallization. Are you with me? So you should have different solubilities at different temperatures. That way, we can dissolve everything at certain temperature, and then when you change the temperature, something falls out of the solution, which will allow you to separate. That is a solvent you're looking for. For different compounds, it will be a different solvent. You need to figure out what that is. So the ideal solvent also dissolves all the impurities at warm, high, and low temperatures. Remember the concept which we talked about. Both of them are soluble at warm or hot temperatures. At lower temperatures, one of them is soluble, not both. That is how you separate it. Both of them are insoluble, both of them are soluble at 0 degrees, then how do I separate? What is the purpose of recrystallization? Just think about it. Right? So you're looking for that ideal solvent, and there are ideal solvents. This is done very much. Now you figured out your solvent, whatever that solvent. So I'm not using water anymore, I just say hot solvent, whatever your solvent is. It can be acetone, it can be ether, it can be DCM, it can be water, whatever solvent of your choice is. So I heat the solvent because I'm trying to dissolve this at hot temperatures, the compound. I'm trying to do it at hot temperatures, then I'll cool it, then I'll filter it. That's a point. So I take this, put it on a hot bath, the hot solvent, I pour it slowly into this. I get my solvent in. Remember, as much needed only for solubilizing your compound. Once it is dissolved, you're done. Okay, keep it warm, remember, so that you can dissolve the entire compound. It is soluble at higher temperatures. When you cool it, something falls out of solution. You're not ready for that yet. So I need to keep it hot. So can I just crank up the hot plate? Just heat it up, keep it warm. Can I do that? What do you think? Sounds like fun. Maybe we should try doing it. Nah. Because as you heat it, you are solubilizing the compound, surely, but aren't you evaporating the solvent at the same time? If you're heating it to the boiling point of the solvent, isn't solvent also evaporating out? So aren't you changing the solubility? You're supposed to have enough of the solvent to dissolve your compound. But if you're heating it too much, the solvent starts boiling and starts evaporating. If you're heating it so much that it is boiling, then obviously you're evaporating the solvent. So you do not have, if you keep doing this, not noticing it, at some point you'll have less solvent than what is needed. Then what happens is, when you cool off, along with the compound you need to recrystallize, you'll also have some amount of this coming out of the solution because you do not have enough solvent. Are you with me? So your recrystallization will be impure. You will not get a pure product. You'll have some amount of Z with that X which you're supposed to have pure. Are you with me? So you do not want to do that. Again, patience is key. So solvent height, heat dial too high. See what happens to the solvent height. So you do not have enough solvent for it to be soluble at high temperatures. That is something which you like to avoid. Something which you should not do that. Do not overheat. Evaporation is a physical property. We cannot avoid evaporation. Now this is a bigger picture. So you take your impure solid, dissolve it in minimum amount of hot solvent. The important points are highlighted there. Then filter by gravity while still hot. Allow to cool to room temperature, right? Allow to cool to room temperature slowly, steadily. Cool to room temperature and then cool to 0 degrees. Not directly from here to there. No. Now you have your crystals in this. The solid should fall out of the solution. Then filter it. There is your pure product. Dry it. Leave it on a watch glass. Remember to weigh that filter paper. Do not forget to weigh that filter paper before you filter it. So filter it, leave it in a watch glass, let it dry, and then when you come back next week, you are going to weigh it. Are you with me? Questions, concerns? Okay. So, melting points. The second part of the experiment is melting point. Determine the mass of all compounds recrystallized and isolated. Determine the melting point of all compounds for identification. You are going to do melting points for all the compounds you identify, isolated. Now, this is a simple a benchtop instrument which you'll see almost on every bench or an alternate bench in the lab. You can't miss seeing this. You'll see. And then all you do is you're trying to get the melting point. Using this apparatus, you measure the melting point of a given compound. So how do you put this compound into this? So there is a capillary tube. Your TS will provide you this, or you should have them. TS will provide this. The capillary tube is closed at one end, open at the other end. So you have your compound on the watch glass or a filter paper or something. So you have your capillary which is closed at one end. It's much thinner than this. It's a thin thing, but I don't have anything else to show it. So I'm using this. An open end. So you take a little bit of compound into this and then tap it. Tap it gently so that you're getting a little bit of compound to the bottom of your closed side of your capillary. Are you with me? You can visually see it. You can visually see the compound. Then tap it gently onto it so that there are no gaps between the crystals of your compound. Are you with me? Simply speaking, pack it tight. That's what I mean. Just tap it gently on the bench top. Don't tap it that it breaks and then it hurts your fingers. It breaks, I don't care. When it hurts your fingers, I do care about that. Just tap it gently so that all the solid settles down. Now take this capillary, place it in this. There is a spot there for these capillaries. There's tiny holes in there. Just take your capillary, put it in there. And then if you visualize through this, you can see it through that. You can see that capillary bottom. It is zoomed in, very much zoomed in, and you can see the solid, crystal clear. Okay, it is zoomed into that bottom of your capillary. Now what are you doing? Then heat up the temperature. There is a dial there which you can turn up the temperature using with. So as you increase it, as you rotate it, the temperature keeps rising, and you can read the temperature from the thermometer which is there. This thermometer can be used for reading it. So what are you looking for? Keep looking through that through the magnifying lens which you have on the melting point apparatus, you can see the bottom of your capillary tube where the solid is, and then all you're looking at is the temperature where it starts melting, temperature where it is completely melted. Starts versus completely melted. That is known as a melting point range. All the compounds have a melting point range. You cannot report melting point as 150. No, it is 149 to 151 or a longer range based on what your observation is. Just read the temperature from that thermometer there. Starts melting, you can see it. Trust me, after this experiment, you'll come and tell me what I was talking about. You can see it clearly. Starts melting, it starts melting. You can see the liquid appearing and it's completely melted. So that's the temperature range you're trying to note down in your observations. Right? That's how you get the melting point for any number of compounds. Now, once you take a melting point for a compound, turn it off. Make sure the temperature of the melting point is 0 when you get back there. If the temperature is already at a certain temperature, right, you do not know the compound melting point. So when you put the capillary, it might melt. Then you miss that starting melting point. So you want the melting point apparatus to be cooled down. So once you're done, please make sure it is turned off for the other person so that they can use it. If not, the other person has to wait until it is cooled down and please do. Just be a little responsible for yourself and for the other people working in the lab. Simultaneously with you. So this is exactly what I told about. Now, along with this, remember there are post-lab questions. I walked you through that process anyways, so you can read through it. But there are post-lab questions you should include into your lab report. I will post those post-lab questions via Canvas announcements by Friday. By Friday, okay? So that you can include those, answer those post-lab questions, include them into your lab reports. Are you with me? So wait for the post-lab questions, they'll be posted every week for every experiment by Friday of that experiment's week. By the Friday. So you are going to submit your lab report to a TA in the corresponding section. When is your lab report due? Now here it is. Here we are this week, February 5th. You're doing your lab 1. This week you'll finish your lab 1, right? You'll do your lab 1 and you'll finish your lab 1 next week. That is February 12th. You will weigh the mass of your filter paper. Remember, you'll leave it for drying until next week. Come in, weigh the mass of the filter paper, then the mass difference of your filter paper and filter paper with the compound gives you the mass of the compound. That is what you use for calculations, for percentage recovery and all that. And then you measure the melting point of your unknown compound, the mass you have in the filter paper, you get the melting point of that and tell me what your compound is. What was your unknown? What is your unknown? Based on the melting point. Are you with me? Am I making sense? And you will finish your experiment next week. You will start your experiment, do everything except drying and getting the melting point. That you will finish next week. And then you have a week's time to finish your lab report. So make all those observations and then turn in your lab report the week of February 19th. So 2 weeks from now. You're going to collect the data. And that is the reason why it is essential you note down your observations because you would not remember for 2 weeks over a period of 2 weeks. I don't know, I would definitely not remember. If it is me, I would definitely forget things. Oh, I can assure you that. Again, just I've included this, what should be included, what should be written down. So please go through this. We have talked about this during the first week of classes, but still I've included them again for your reference. When you're writing these lab reports, go through them. If you have any questions, your lab report is not due until the week after. So if you have any questions, I will walk you through this next week also. I've gone through this briefly last week, but again. That's it. I'll see you all next week for recitation. Can I have those attendance sheets back, please? Whoever has them, can I have